And now for something a little different. Section 9.5 starts with Gauss quadrature. Everything we've done so far has been really based along a set of given points. You can be delivered a data set through experiment, you can be delivered a data set through a set of functional evaluations performed by someone else, and they want you to integrate through that, or perhaps some intermediate process in a numeric algorithm requires you to do the same. Gauss quadrature asks a different question, or approaches numeric integration from a different perspective. If you have the option to call a function at any point you want, whether this is some sort of weather numeric algorithm, whether this is an experiment where you're deciding where to grab the data points from, where are the optimal points to source, and what are the optimal coefficients to apply to get the best integration method possible. So if you think about it, let me go through in a little nice table here that the rectangular, midpoint, and trapezoidal equations all really kind of just by default look at endpoints of regions, middle points of regions. They continue on here to look at Simpsons, which really is kind of both endpoints and all the middling points. And they're kind of integration methods taking the grid spacing and the number of points given to them. Never really asking the broader question, what point spacing would be ideal to obtain a perfect integration of the region. So the general form formulates this question uniquely. So it's integration from a to b of f of x dx. So that's just integration general form equals now the summation of some unknown set of c coefficients and an unknown set of functional evaluations at points x of I that we are free to establish. Again, so the number of these quadrature forms on the right hand side is up to us to determine. In each quadrature form, like if it's a 2-point evaluation, comes with an unknown coefficient and an unknown functional evaluation x location. So if you want 2-point quadrature, it's actually 4 unknowns. If you want 3-point quadrature, it's 6 unknowns. If you want 6-point quadrature, it's 12 unknowns. So how do you account for all these unknowns? This really just seems like they're making this blank slate and then you're going to fill it in with magic? No, perhaps I'm being a bit silly about it all. They make a set of sample training equations with known solutions that you can train these coefficients up, just tune the entire set in a specified region. Notice that all of these integrations are performed in a particular region, -1 to 1. They're centered around 0. So this is Gauss quadrature within a specified region. These equations are somewhat arbitrary, though you see they just tend to take the increasing polynomial orders. So for this first example problem where you have 2-point quadrature, then you actually have 4 unknowns and need 4 equations. So the first 4 polynomial orders are listed as examples, whose integrals we can readily determine between -1 and 1. And so this gives us now 4 equations, 4 unknowns. So you can put that in matrix form, invert, multiply, use your favorite method, whatever you want to do, and you figure out what the exact C1 and X1 locations are that give you all 4 of these estimates perfectly. And this is what comes out. So you get a C1 equals to 1, C2 equals 1, and then the X locations are given as -1 over root of 3 and +1 over root of 3. It's kind of these interesting, somewhat non-intuitive locations to sample the equations, but when you plug it back in as an example, x squared, which is what they've gone through here in example, you plug back in those locations to integrate. So there's C1 of 1, C2 of 1. There's the X location sample, the X2 location sample. You get the exact value of the integration of x squared from -1 to 1. That shouldn't be surprising because it's one of our training functions. If we didn't get the exact value, then that means you've done the matrix math wrong. But the real test comes in whenever you do something that is not one of the training quadrature functions. Like I think the example they go into is cosine. So for this case, where you have 1s and the sampling location given, if you wanted to integrate the function cosine from -1 to 1, you get an answer of 1.67582366, which if I can really quickly look at the eventual form, you get the real answer is like 1.6829. So already, just with 2-point quadrature, you have approximated the actual solution down to a very small percent error, so 4.2%. And as you might imagine, and you can see where this is going. We'll probably even see a little bit over here on the next page. But for now, we're going through the progression. What happens if you go to 3-point quadrature? You suppose the solution is the form here, where you have 1 unknown point, 2 unknown points, 3 unknown points. Both the coefficient and the sampling location are unknown to you. You go through the same evaluation, except now instead of just doing 1 through x cubed, you have to step up your sample training functions all the way up to x to the 5th. So 1 through x to the 5th to make 6 training functions for the 6 unknowns you need to define. The leading coefficients are now non-unity, so 0.5 repeating, 0.8 repeating, 0.5 repeating for C1, C2, C3 respectively. And then the x sampling locations, keeping in mind that these are normalized to a domain of -1 to 1, are given there. Probably not a big surprise that the middle sampling location is x equals 0. Everything is fairly evenly biased around 0. It's symmetric for every case given in the textbook. So again, they evaluate the cosine function, taking the general form there, placing the function to be evaluated, replacing it with cosine here, to obtain a value of 1.68285. You can read the rest of the decimal places, and that's actually off by about 1/10,000th of a decimal place. So Gauss quadrature can be a very, very accurate numeric method if you are able to cherry pick the locations you sample your function. The known coefficients for 2 through 6-point quadrature are given in table 9.1. The same formula is extended, the same you see in equation 928 and others. The general form being up here in equation 930 is just extended the number of points you select. And really the only complicating factor with quadrature is how you use it to integrate functions that have bounds other than -1 to 1. It requires a change of variable. And this is covered most descriptively, I think, in example 9.2. The definitions you need are the definitions for x and dx, and they remap those into the variable t. So the definitions are first given up here in equation 931, probably something you want to highlight in your book, because in this example they'll be taking an exponential function, e to the -x squared, from 0 to 3, and using 4-point Gauss quadrature, evaluating the integrals. So the rest of the quadrature steps, turn the crank, it's all done. But what's interesting is how they remap. So x equals 1/2 t times b minus a plus b. So those are all just bounds. A and b are the left and right hand sides. So this gives you the output of 3/2 of t plus 1. And then you do the same thing for dx. You get 3/2 dt. And then you just plug it straight in. It's nice to have that formulaic result. So this is our source function. You end up plugging in for the x, that form calculated here. So instead of being e to the -x squared, we get e to the -3/2 t plus 1 squared. Be sure to put that all in brackets and get things right. Instead of dx in the integration, you just replace with dt times 3/2, which is placed in the leading circumstance, and that successfully remaps the equation from -1 to 1 instead of being from 0 to 3. So now that those bounds are remapped, you can solve with the standard quadrature coefficients developed and trained off of the appropriate number of polynomial leading elements. So quadrature can be very precise, but it has the requirement that you're able to sample a function wherever you like, and you also then have to remap coefficients into a region that matches your true integration purpose, because very seldom are you going to conveniently want to integrate from -1 to 1. Kind of the last subject in the integration chapter is how to do it in multiple dimensions. The easiest way to do it in multiple dimensions is just to integrate once across, say, the x direction first, tabulate those results in another array, and then integrate that across in the y direction. It's very simple to do square regions, but this process discusses non-square regions. At which point you could, if you felt so diligent, tabulate and formulate the Simpson's 1/3 rule, except instead of having coefficients or functional calls as the source, you end up having entire integration forms as the source coefficients. So overall, I generally would advise to try to stick with square integration regions. There are a few MATLAB functions that can be helpful to you. First and foremost, the quadrature integration function is probably the principal integration form used by MATLAB if you have a function you can actually call. Namely, this function also needs to be more or less one-dimensional. The integration limits are specifiable, but if you use the base quad function, that is really just a one-dimensional integration between points A and B. It handles remapping, handles other things for you we just discussed. There's a modification of quad, it's quad L. Let's use a slightly different adaptive method, so the differences are quite small. So functionally, quadrature in MATLAB is a function you'd want to use that's built in automatically. If you want to use trapezoidal integration for something that's a bit quicker, perhaps you have a data set and not a function you can call, trapezoidal integration of x and y is given to you there. But if you really have multidimensional forms that you need to take care of, the double quad function is how to take care of it. And as the input clues you in, xmin, xmax, ymin, ymax, square regions. Each one of those inputs has to be a coefficient. So if you go from an x of 1 to an x of 4 and a y of 1 to a y of 4, well, that's just a square region. You can't be overly creative with the integration bounds in this circumstance. So some inbuilt functions to make everything behave rather nicely.